Okay, and welcome back to part 2 of 3.5, where we're going to look at the last 3 problems from this section. So we're going to explore 2 different type of cones, and then we're going to look at your shadow. Okay, so example 9, sand is poured on a beach, creating a cone whose radius is always equal to twice its height. If the sand is poured at the rate of 20 inches cubed per second, how fast is the height of the conical pile changing at the time the height is 2 inches? Okay, so first thing we're going to do is draw a picture. So what you need to do is you need to visualize yourself pouring sand in the shape of a cone. Okay, so what would that look like? So hopefully you get something like this. Okay, so there's my sand, and again, I'm just going to I already know to label stuff just hopefully from remembering from geometry. I have the radius and I have the height. Okay, so we know what we're going to fill in. What are we given? What do we need to find? And what formula should we use? Okay, so I know the radius is always equal to twice its height, so they're telling us that, so we should probably write it down. So the radius is equal to twice the height. If the sand is poured at a rate of 20 inches cubed per second, so sand is poured at a rate of 20 inches cubed per second. So here is like, well, what would I label this? Okay, well, the key word here is actually going to be in the label. I have inches cubed per second. Well, when I think of something being cubed, what do I think of? Hopefully, we're thinking volume. So dV dt, okay, and is going to be 20. Okay, and then let's see here. How fast is the height of the conical pile changing at the time the height is 2? So how fast is the height of the pile changing when the height is 2? Okay, well, the height is 2, so I'm going to go ahead and put that there. And I need to find they want to know how fast is the height changing, so that's dH dt is what we need to find. So now I need a formula. Well, I have, talking about the height, I have a volume, I have a cone, so I need the volume of a cone, which is V equals 1/3 pi r squared h. Okay. Now, here's the thing. So there's a reason why they gave us this, that the radius is 2 times the height. If I'm looking at this equation, I have 2 variables, r and h. I would technically have to be using my product rule. And again, I'm kind of leading you into this to know how to set it up. If you're doing this on your own, you might end up taking the derivative using the product rule. The problem is they don't mention anything about dr dt. I know nothing about that. So I would have 2 unknown variables and I would not be able to solve it. But they give us this fact here. I'm trying to find dH dt, so what I'm going to do then is I'm going to write this equation in terms of h. So for r, I'm going to plug in 2h. So then that ends up giving me 4/3 pi h cubed. So one thing when you're working these problems out, don't be afraid to try stuff, and if it doesn't work and you're missing a variable and you can't solve for it, go back to the equation and say, okay, you know what? Maybe I need to see, can I write a variable in terms of another variable so I can solve this? Again, that's going to come with practice. And you can't be afraid to try something and it not work. Okay, so now let's take the derivative. So I have dV dt is equal to 4/3 pi. Well, the derivative of h, okay, well, that's 3h squared dH dt. Well, I know the 3's are going to cancel, so I'm just going to write this as 4 pi h squared. Well, that's 4 dH dt. That's what we're trying to find. and dv dt is 20. Well, if I divide that over, I get 20 over 16 pi. And labeling it, so dh dt is equal to 5 over 4 pi. And I'm talking about a height, so it's just going to be inches per second. Again, so if I were to write this sentence out, I would say the height of the sand pile is increasing at a rate of 5 divided by 4 pi inches per second when h is equal to 2 inches, or when the height is equal to 2 inches. Okay, so there is one type of cone problem. So you definitely should know the volume of a cone. I think that does help here, because we do see these problems quite a bit. AKA, we're seeing it again. Okay, so we're going to talk about this time it's draining. So water is draining from a conical tank with vertex down, okay, at a rate of 2 meters cubed per second. The tank is 16 meters high, and its top radius is 4 meters. How fast is the water level falling when the water level is 12 meters high? Okay, so first thing I'm going to do here is I need to draw this picture. As soon as my pen decides to work. There we go. Okay, so I have a cone. Not this again. Okay, so I have a cone. Its vertex is down. Okay, so again, I'm just going to kind of draw this in. I have a height. I have a radius. Okay, so let's fill. So I have a given. What do I need to find? And formula. Okay, so we know it's draining at a rate of 2 meters per second squared. Okay, so again, I'm going to look at that keyword, meters cubed per second. So again, that's going to be that volume. So dv dt, well, it's draining, so that means it's going to be -2. I also know it's 16 meters high, and its radius is 4. So let's just add this in. So again, this is a constant. So the tank height is 16. Its radius is 4. How fast, keyword for related rates, is the water level falling? Okay, so that means I'm figuring out that height. So dh dt, when the water level is 12. So this one's a little interesting. So I'm just going to put this here. When h is 12, okay? Because we're given two different h's here. So I need a formula. Well, we're talking about that volume again. So the volume is equal to 1/3 pi r squared h. Well, we're running into that problem again. I have two variables. I know if I do the product formula, I'm going to have a dh dt and a dr dt. There's nothing talking about that rate of the radius. Okay, I can't say the radius is constant, because if you think about it, as the water is draining out, the radius of the water is constantly changing. So my r is not a constant. So I need to get either r or h in terms of each other. Well, since I'm need to find dh dt, I need to keep h. So I need to find a way to relate r and h together. Well, I'm going to go back to this original thing that I know here. I know when r is 4, h is 16. Okay, well, if we go back to geometry and think about similar triangles, I know my ratio of the radius to the height is 4 to 16. Okay, well, if I cross multiply, I get 16r is equal to 4h, which means r is equal to h divided by 4. Well, now I have r in terms of h. Okay, so this is what that meant in those guidelines where it says sometimes you're going to have to find it. And that's what I did here. Okay, so again, it just comes from practice and knowing, okay, well, if I take this derivative, I need to have I'm going to have 3 different rates. Do I have all my rates? Well, I did not. So in that case, and since nothing's constant, I knew I needed to write a variable in terms of the other. Okay, so let's go ahead and plug this in now. So I have 1/3 pi h over 4 squared times h. Okay, so this gives me pi over 48 h cubed. So now I can go ahead and take the derivative. So I get dv dt is equal, well, I'm going to bring down the 3, so that becomes pi over 16 h squared dh dt. Now let's go ahead and plug everything in. I get -2 pi over 16. Now here's where you have to be careful. This is h squared. So you're like, well, some of you might have plugged in 16. I need to know how fast is the water level falling when the water is 12. So that's why we have 2 heights. So I'm plugging in 12 here. And then dh dt, what we need to find. So this one is a tricky problem. Okay, well, let's divide everything over, get dh dt by itself. So dh dt is equal to -2 over 9 pi meters per second. That was a tough one. So the water level is falling at a rate of 2 divided by 9 pi meters per second when the water level is 12 meters high. Okay, so last problem. I would recommend trying this one. Okay, see how far you can do by yourself and then coming back and checking. Or if you feel like we can do A together, pause it, you try B. Whatever's easiest for you, but you should try to do one by yourself. Okay, so last example, me and my shadow. So suppose a 6-foot tall person is 10 feet away from a 10-foot tall lamppost. The person is moving away at a rate of 3 feet per second. At what rate is the length of the shadow changing? Okay, so lots going on here. So let's just go ahead. I have my given. What do I need to find? My formula. Okay, so we have a 6-foot tall person, 10 feet away from a 10-foot tall lamppost, and they're moving away at a rate of 3 feet per second. Okay, so I'm gonna label from here to here. I'm gonna say this is D, and I don't like X. I'm gonna use S because that's my shadow. Because if you think about it, I'm looking at my shadow. If the lamppost is behind me, my shadow should be in front of me. So that's why I'm gonna label this S instead. Okay, so you're walking away at a rate of 3 feet per second. So I'm walking away. So that means my distance is changing. So this is so that dt is equal to 3. And again, because I'm moving to the right, that's why it's positive. Okay, so that's 3. I need to find at what rate is the length of the shadow changing. So ds dt, that's what I'm trying to find. Okay. So you're like, well, what formula do I use here? Hopefully this will trigger something from geometry where we did shadow problems, and that was in our similarity unit. So in this case, I'm going to be using similar triangles. So how that would look is I would say, and remember, when you write ratios, there's a couple, ratios or whatnot. You can write it however you want, just have to make it consistent. If I start with the top, if I start with the big triangle, then I have to do the big triangle. So I'm going to say 10 is 2/6 as d plus s is 2s. Okay, so now, so that's my formula. Obviously, I'm going to want to simplify that a little bit, so I'm going to cross multiply. So I get 10s is equal to 6d plus 6s, which means 4s is equal to 6d. Okay, so let's see here. Do I have a dsdt? That's what I'm trying to find. dd dt, have that. We are good to go. So let's go ahead then and take this derivative. So I have 4. Okay, the derivative of s is 1, so ds dt is equal to 6 dd dt. Okay, well then I have 4. Well, we need to find ds dt is equal to 6 times 3. So ds dt is equal to 18 over 4, which is 9 over 2. So it's changing at 9 feet per second. And if I were to write this, I would say the length of the shadow is growing at a rate of 9/2 feet per second. Okay. Let's go to part B. At what rate is the tip of the shadow changing? So it's kind of a weird thing to think about. So that would be, if I'm looking over here, where is that? How is that changing? Well, to figure out how fast the tip of the is changing, I would need to add the two rates together. So I'm going to take, so the rate at the distance is changing plus the rate of the shadow. Well, dd dt is 3 plus ds dt is 9/2. If I add those together, I get 15 over 2 feet per second. So the tip of the shadow is moving away from the lamppost at a rate of 15.5 feet per second. Okay, so that's it for related rates. If you have any questions, I know that worksheet can be a little bit long. You have till Sunday though. Make sure to ask me some questions. Have a great day.